All right, everybody, I think it's about 2 o'clock. I would like to go ahead and get started and welcome to another new week. I hope that you guys all had a great weekend and are managing to juggle everything. We're almost a month into the semester now, so it starts to ramp up eventually, get us a little bit busy. That includes me. I get pretty busy too, but I just want to take a minute to go over a few comments before we actually get into the math today. First of all, there is homework due tonight. It's a short assignment for the most part. But I did want to mention, I sent an email out about this. I am not going to be able to be at my office this evening like I normally am on Tuesday nights. This is a one-time only thing that I can't be around. So if you have questions on the homework that's due tonight that you want to ask me about, your best bet is to make sure it's on that whiteboard over there, at least by during the break today. I will take time to answer the questions that come up. So we can almost do as many problems as you want. I want to just make sure that it's nice and easy for you since I won't be able to hang out at my office later tonight. That's just today only. On Thursday, I'll be back to normal. I'll have my office hours all day on Thursday, and I'm going to have hours on Friday as well this week. So that should be good. That might be especially of note for those of you who have not stopped by to introduce yourselves to me yet. Remember in my email, I also mentioned this is the last week you can actually just stop by for 5 minutes to say hello. I want to check off your name. I want to make sure I know who you are and that you know where my office is. You can do it in Zoom or in person. Obviously can't do it today because I'm not going to be in my office later today. But later in the week, you should definitely do that. By this weekend, I will probably be sending out an extra credit quiz that will be sort of tied up with the midterm that's coming up. And you're going to want to be able to do that extra credit quiz. You can only do it if you have done the little intro thing. So stop by if you haven't on Thursday or Friday and just say hello if you would. Okay. In addition to that, there is also going to be an assignment due on Friday. So I've chopped these assignments up to be fairly short, but they're coming pretty steady. Friday's assignment has a few more problems on it. When you first look at it, you're going to be like, oh, that's a bit more work. Actually, it goes really fast. The topic for Friday's homework is super short and shouldn't be too crazy. There's a chair there, if that works for you. I don't know if there's another seat or not right at this moment. You okay back there? Yeah. Okay, make it work. Okay. Yeah, so there is a homework assignment due on Friday. I'll have office hours Thursday and Friday. And if you start by Thursday, you can even ask me questions in class about it on Thursday. So that's kind of where we're at this week for homework. I want to jump ahead, though, to next week for a minute because we have an exam next week, our first midterm. It is on Thursday next week. So I have pulled up our Canvas page here, and I wanted to direct you to some things that you can start looking at as you have time in these next few days. Like I said, the homework this week is pretty short, so I'm hoping that you'll maybe have a little bit of time. If you go into the Files section of our Canvas page, right? I want to click on that right now. There is a folder down here that says Midterm 1 Resources. That might be a little bit hard to read. Midterm 1 Resources. I'm going to go ahead and open that one. And wow, if you look in here, let me pull it back out again. Smaller. There's quite a bit of stuff in here. Now, the reason that all of this stuff is here isn't because I think everybody needs to spend 500 hours looking at everything that's in here. It's more just that I would like to try to be a good professor and give you guys some resources to help you look for the exam that's ahead. It doesn't mean that everybody needs to do everything in here. Nothing in here in this folder is required. It's all just optional gravy on the side. If you're solid and you know the stuff and you don't need to look at all this, no worries, you don't have to. But I want it to be here in case it might be of help to some of you. So I wanted to just tell you what's in here. If I could only do one thing to study for the exam next Thursday, if I only had time to do one thing, what I would do is I would sit down for 2 hours with one of these sample midterms. So these are actual midterms that I have given in this class before, and there's 2 of them. One of them is in all caps. It says first midterm sample, and then right above it is first midterm sample solutions. So you can read my worked out solutions in detail, but I wouldn't recommend doing that until you actually try the problems yourself, right? So you've got a sample midterm there. There's another one that's in the all lowercase. So first midterm sample 2, and then the solutions to that as well. So 4 of these files are just sample midterms with solutions. I would recommend that everybody at least do 1 sample midterm. It'll at least give you an idea how long the test would be, what kinds of questions I might ask, get you a little bit in the right framework of kind of what might show up on your exam. Obviously, your exam will be different, but at least the structure. And I'm going to give you the full 2 hours next Thursday to take this test, which is exactly what these exams were prepared for. So it's exactly how I did it in the past. Anyway, so there's a couple of sample midterms there. If you had a little more time, what you might do is try one of them. And then when you see what maybe some of your weak spots are, or things that you're not as comfortable with, study those up a little bit and then try the other one. Not that they're going to be exactly the same, but at least, it gives you something to sort of shoot for, okay? But try to do it without just reading my solutions. Try to do it without just, being all distracted and like have 10 other things going on in the background. Try to, treat it like it's like an actual test so that you get a little bit of practice with that feeling. What else is in here? Down at the bottom, there's also a review session. So a few years ago, I actually made a video of me solving a bunch of sample problems for this midterm. So if we open up this file here at the bottom, it says just review session first midterm. I can just show you kind of what it's about. There's also a little overview here. I talk about, okay, the first chapter will be about 40% of the midterm. I don't know if you can read this in the back, but chapters 2 and 3 would be about 60%. I've got a list of some of the important formulas. So if you need to make some flashcards to start learning some of these things, like, for example, the differential equation for Newton's law of cooling would be one. The change of variables for Bernoulli differential equations would be another thing you need to know cold going into the test. Today, we're going to talk about the cofactor expansion formulas. So there's a little bit of a list, about 10 things here that I thought would be good to know. But then the real thing that I did here is I came up with some practice problems. So I think there are like 7 of them here. So you could take these 7 practice problems, and again, this is optional. If you don't have time for it, or you just want to focus on the sample test, that's okay. But what I've got here is some extra problems that you could try out. And the thing with the review session is, instead of just reading my solutions, you can do that. My solutions are typed out right here for the review session. But the other option is to go to Pages, because in the Pages section, it lets me load videos. And so you could just go to midterm 1 review session. I broke it up into 3 30-minute little segments of video. So if you actually watched the whole thing, it would take you an hour and a half. Again, you don't have to do any of this. Or maybe you see just some of the problems that you're concerned about and you want to watch a video on that. So this is here for you. Take it or leave it kind of thing, if you think it might be helpful. The other thing I have here, let's go back to the files again, back into this resources folder. I also have just a review packet. And the review packet needs to be fixed because I put the wrong date for the exam up here. The date is next Thursday, which is September 25th. I think this says this is February 18th. So that must have been from last year. Anyway, ignore the when and where on this sheet. But what it has here is a bunch of information about the exam. Office hours, I am going to have some extra office hours next week. Like normally I don't have office hours on Wednesdays, but next Wednesday I will because we have the test on Thursday. I'll let you know what those hours are as we get a little closer to the exam. And then just what the exam is going to cover. In each of the chapters, I wrote sort of a glossary of words. These are just things to kind of read through and check them off. Say, oh yeah, I know, what a linear differential equation is. I know what row echelon matrix is, things like that. And just kind of make sure there's no surprises in this list of words. And I have it for all 3 chapters. Today we're going to focus on chapter 3 mostly, which is here. It's a shorter chapter. I also organized it in a little bit of a different form as a things to be able to do list, kind of a bullet point list. And again, you can kind of use it like a checklist. Just go down the checklist and ask yourself, okay, would I be able to do these things? Quite a few things here, right? Can I solve Newton's law of cooling problems? Can I solve Bernoulli differential equations? Can I convert a matrix into row echelon form by doing EROs? All these kinds of things that should sound kind of familiar. But it does go on, it goes all the way into the next page. And of course, we haven't quite gotten to all of the last part of the list yet, but we will this week, finish chapter 3. Then I've got some advice for how to focus on this exam. I wanted to mention one thing specifically here. Let me highlight this little paragraph. I know it's a little hard to read probably, but let me read it for you. This is about chapter 1. You might remember in chapter 1, you were learning how to solve separable differential equations, and then linear differential equations, and then Bernoulli and homogeneous differential equations. But in each section, you were always, doing the same method on the same type of equation on the homework. So everything in section 1.4 was separable. Everything in section 1.6 was separable. And unfortunately, that gets you a little bit trained in to like, oh, on this section, I'm going to do all the problems this way and so on. But the exam is not going to be like that, right? The exam is going to say, here's a bunch of differential equations. Tell me what they are. Are they separable? Are they Bernoulli? Are they homogeneous? Are they linear? Whatever. And then solve something from that list is likely what I would do. So to help you practice just kind of dealing with mixed up problems, in the review chapter, in the review section at the end of chapter 1 in the book, there's sort of a big whole hodgepodge of problems that have been like thrown in, mixed together. And so I mentioned here problems 16 through 42 of that review in the back of chapter 1. You might go through some of those and just try to identify them. Is it linear? Is it Bernoulli? Is it homogeneous? Is it separable? Especially if this is your weak point. Right, if you try the sample exam, you think that's what I'm going to do, and then you realize during the sample exam that your big problem is you are not identifying the equations very effectively, then this might be something for you to follow up with to sort of strengthen that part of your preparation. And those problems 16 through 42, I actually copied the solutions to all of those. So if you go back, let's go back to the for the resources. The very first one here, chapter 1 review problems, I just did a big photocopy of the solutions to all of those. These are in the chapter 1 review. So you can just look through, like number 16 says it's separable. Okay, so see if you figured out that was separable. So you can go through and just do that. I don't think anybody's going to want to solve all 25 of these extra problems, unless you really don't have anything else to do. That's a lot. So just take it with a little bit of a reasonable dose of this stuff. Don't feel like you have to do everything. Actually, you should make sure you get good rest, take care of yourself and all those things too. You can overdo it on this front and then not feel like you're feeling good physically for what you have to do. So just take it easy. Don't get overwhelmed by all of this stuff. In the midterm 1 resources document, there's also some additional extra problems there too, as if you didn't need any more. And I have the solutions to those here as well. So anything that I've put out there, I also have the detailed solutions for. So it's never just going to be figured out on your own. I'll have answers to look at. And at any point, if you're not following something from my solutions, stop by my office hours and I'll try to clear it up for you. But yeah, again, my big takeaway here is this is all optional. I would highly recommend one sample midterm for everyone. And then depending on how that goes, maybe another sample midterm, maybe focused studying in certain things from this list that hits more on where your weak points are. And I think that will really, really help. I obviously want everybody to do well. We're all on the same team here. We're all trying to climb this mountain together. So I hope that you will let me know how I can help make that happen. Like to do that. Does anybody have any questions about this? So just so you have just a little bit of an advanced heads up, I'm going to give you an extra credit quiz. And this is for everybody who's stopped by for 5 minutes to say hello. Probably this weekend, I will send that out and I'll give you a couple of days to work that out. You'll be able to earn about 3 points for the midterm. It's going to be a 100-point exam. You'll be able to earn about 3 points towards your midterm by doing the extra credit quiz. In addition to that, after the exam is over, the exam is next week on Thursday, that following weekend, I'm going to have you guys watch a video that introduces chapter 4. It's kind of a long video, but all you'll need to do with it is take notes on it and turn them in, and you'll get additional extra credit points towards the first midterm. So probably another 3 points. So by the time it's said and done, you'll be able to get about 6 points or so of extra credit, which makes a difference. Every point counts, right? So anyway, it'll be broken up in 2 parts. So just so you know that the weekend after our midterm, which is actually 2 weekends from now, there'll be a video to watch, but there won't be any other homework to do at that point. So shouldn't be too crazy. Questions? Okay, let me mute that off so that I have space here to fill up my boards as I always like to do. I think I've gone over all my announcements now. I forgot my little camera tripod. I normally record my lecture in the morning class. There's a reason that I do that in the morning class and not your class. And that's because sometimes I feel like, well, if there's a technical glitch in the morning one, then I can still do it in the afternoon. Well, I screwed up this morning with my recording. So I'm recording my lecture today here on my phone, and I'm using my handy dandy hand sanitizer as my tripod, since my tripod I left with my car today. So it was an interesting morning. Anyway, let's see. What do I want to do? I would like to bring you guys back to where we left off last Thursday. Also want to suggest, I should have suggested it before now, but this is just for the future. Before you come into class every Tuesday especially, it's really a good idea to kind of go through your notes again from the previous class. I mean, it's been 5 days, right? If you've kind of been checked out over the weekend or been doing other things or whatever, it can be kind of an abrupt re-entry on Tuesday to come back in and just pick things up right where we left off. I, of course, will try to help with that by doing these recaps, but I also want to just really encourage everyone to just glance through your notes for 10 minutes before class, especially on Tuesdays, so that you kind of got things back in your mind a little bit. One of the things we did last Thursday before we took a break for the weekend was this invertible matrix theorem, and I really need to come back to it again. It's really important. It is in a section, I think it's 2.8 in the book, that will not have any homework for it. Somebody asked me, well, so if there's no homework on it, will it be on the test? Well, if you start looking at my handout, you'll see, yes, this is very much discussed in my review materials. Even though there's no homework on it, it's really, really important to sort of understand, what invertible matrices mean from many different perspectives, like different ways of understanding it. It will really help you out. If all we do is find inverses by doing the Gauss-Jordan method, then what we become is we sort of just become ERO button pushers, if I could call us that, where we don't really know what we're doing. We're just kind of like going through the motions of the practical steps, but without really understanding what we're doing. And I want you guys to not just be able to like go through the motions of linear algebra. I really want you to have a solid understanding of it. So this will help with that. This is a good conceptual summary about invertible matrices. So first thing is, remember that when a matrix is invertible, then there's an inverse that you can multiply your matrix by to get back to the identity matrix. That's kind of the definition of it. So A is invertible if there exists an A inverse, such that when you multiply the A with its own inverse, you get the identity matrix. Right. And then everything else in this list is just another way of explaining what an invertible matrix is. So B and C, basically, when you have an invertible matrix, then linear systems have unique solutions, right? If the coefficient matrix is invertible, then any linear system, that's what AX equals B is, it's going to have a unique solution to it. It's not going to have infinitely many solutions, and it's not going to have no solutions. It's going to have one unique solution, in this case when A is invertible, okay? Right? So that's one thing. The other thing is, if you take an invertible matrix and perform EROs on it, you should get n pivots. Those pivots should go all the way down the main diagonal of your square matrix A. So there will be no unpivoted columns. You won't have any defects like getting rows of zeros or anything like that, right? You're going to get solid pivots all the way down the diagonal. Full rank, right? A has full rank of n right here for an invertible case. Right. Product of elementary matrices, I'm going to let that one kind of slide. We don't really need that so much for what we're doing here, but I just wanted to list it since it is in the list. But part F is important. A is row equivalent to the identity matrix. So this just means I can not only do EROs to A and get it into row echelon form, I can actually bring the matrix all the way to the identity matrix. Right. And that's actually how the Gauss-Jordan method works, as we explained last week. Right. So if you can bring A through the use of EROs to the identity matrix, then on the other side of this block that you're setting up, the identity matrix will actually turn into the inverse of A. And so the A inverse is there. And that's the method that we've learned so far for actually finding the inverse of any invertible matrix. Okay, so that's a good point to remember. All of these statements, guys, all of these statements are either true about a matrix that I give you, or they're false about a matrix that I give you. They go hand in hand, part and parcel with one another. So they're all true or they're all false. You can't have some of them and not others, right? It's all one way or the other, if that makes sense. That's how that theorem works. Questions here about anything as kind of a recap from last time? Yes, Arlene.
For the Gauss-Jordan method, for the A, when we try to solve for the inverse or does the all zero row only apply to the left side, or does it have to apply to both sides?
If you get all zero, a whole row of zeros on the left side, you're basically out of luck. Okay. That actually did happen on one of the homework problems. You are out of luck, and in that case, you pretty much know that, I mean, if you get a whole row of zeros on the left side, that means you're going to come up short on pivots. You're not going to get n pivots. And if that's not true, then nothing here is true. So the matrix is not invertible in that case. Right. Yeah, good question. Anything else? You know what we're missing from this list? I think I told you that this list goes on and on halfway through the alphabet. What we are missing from this list is actually something that's kind of nice and user-friendly. None of these things are really that easy to deal with. So if I give you a matrix and I ask you, is it invertible? It's kind of a pain to like do a bunch of row operations. If I want to figure out the rank, I'd have to do row operations. If I wanted to solve a system of equations, I would have to do those elementary row operations. So all of those things take effort. They are all subjectable to mistakes and things like that, right? So it's too bad we kind of, although these are nice different perspectives on invertibility, they all kind of involve the headache, if you will, which you found out about on last Friday's assignment, the headache of doing a bunch of EROs. So I'd like to add something else to the list today that actually has nothing to do with EROs, that we can then use as kind of a breath of fresh air, a different way of thinking about invertible matrices that doesn't require me to do a bunch of elementary row operations. So we're going to do that. I'm going to add item G right here. We're going to add one more thing to our list. And what it is, guys, is something called the determinant of A. It's written DET of A. And that is going to turn out to just be a number. And the condition here for part G is just going to be that that number is not equal to 0. Okay, so the determinant of this matrix A is really the concept that we're gonna talk about. All right. So let me get rolling with that. This is actually chapter 3. So chapter 3 is the start of determinants. Right, and I guess to sort of give you the idea behind this, before I get too much into the technical details of it, the idea is we're going to let A be an n by n matrix. So let me just start by saying, if the matrix is not a square size, then this entire chapter doesn't even apply. Okay, so if you see a problem anywhere where the matrix that you're working with is not n by n, then you can just totally take determinants off of the table. It's not going to be anything to do with that. Okay, but what we are going to do is we will associate a number. And this number is the determinant of A, DET of A. It's also sometimes written in this alternative notation. I don't like this notation very well because it looks like absolute value bars, but that's not what it is. So you'll sometimes see people put these bars around the matrix for the determinant. I wish I didn't have to tell you that, but honestly, it is pretty standard. So you'll see in other books and other professors probably, they might just put these sort of bars around the matrix. So just have to let you know that. So we associate that number with A, whatever it is. And then as you can see, according to my theorem over here, the invertible matrix theorem, this determinant, if nothing else, there's at least one really good use for it, which is it is a test for invertibility, because as I kind of just got through explaining, A, which is n by n, is invertible. A is invertible if and only if the determinant of A is not 0. So that's a nice little test for whether a matrix is invertible or not. We can just calculate this number. Okay. So it's going to give us a different perspective on the idea of invertibility, because determinants really, they are not organically related at all to EROs. Everything else in that list on the left side, somewhere along the line, you're probably thinking about EROs. But the determinant of A really is not about EROs. And you're going to see today, we're not going to do very many EROs today. So it's a different perspective. It reminds me of a little bit of a funny story. I think I promised you I was going to tell today. So I don't know if I told you guys this. I was a grad student at UC Berkeley. I did my PhD up there in the Bay Area. So it's kind of on the east side of the Bay. Well, while I was there was a professor across the Bay in San Francisco at San Francisco State University. And his name is Stephen Krantz. He's a pretty famous mathematician. He was their department chair for a while. And he actually wrote a book on linear algebra. And the name that Dr. Krantz gave to his book, this is the professor at San Francisco State, he called his book Linear Algebra Done Right. That was the name of the book. And it's still pretty popular. It's used even sometimes in our upper division math major linear algebra course. Linear Algebra Done Right. And I picked up a copy of that book one time and started flipping through it. It's a linear algebra book. And I was like, where are the determinants? And I looked, flipping through the whole book, I couldn't see the words determinant until I looked a little more closely at the table of contents, and I saw that there was a chapter in the back of the book called Down with Determinants. And I asked my PhD advisor about this. I said, what's up with this? He said, oh, that guy doesn't like determinants. And he tried to write an entire linear algebra book without ever doing determinants, right? The entire book. He avoided them at all costs. And according to him, this is linear algebra done right. You don't talk about determinants. You avoid them. You find a different perspective on them. And so that was what he really tried to sell in that book. But then my PhD advisor over at UC Berkeley, he knows the guy and they're friends. He had to take a jab at him because my PhD advisor was writing a book as well. And also had some linear algebra in it. And so I looked at my PhD advisor's book and I noticed there's a chapter called Up with Determinants. I was like, this is not just a coincidence. These two guys are like jabbing each other with their book chapters. Because my advisor really likes linear algebra and likes determinants specifically. So I was like, okay, I can see that mathematicians can even among professional mathematicians, there's not really an agreement about what is the best way to think about linear algebra. And I, of course, had to side with my advisor. And so I think determinants are awesome. My advisor would kill me if I didn't say that. So I at least have to be on his side of the ledger. But just so you know, there are people out there who try their best to not talk about determinants in linear algebra. So what we are going to talk about it this week for sure. It's the shortest chapter in the book. So we will only need a couple of days to kind of talk about chapter 3. But nonetheless, I think it's linear algebra done right is actually this. Just my opinion, but we'll see. Anyway, let's get into it. How do we calculate this number that we are associating with our matrix? I have to explain all of that. So what is the determinant of any matrix A? Well, I'm going to kind of go at this the same way that I worked on inverses of matrices, which is I'm going to start with smaller matrices and work my way up. So let's just give the first answer here. The first answer is just that if my matrix capital A is just a 1-by-1 matrix with a single number in it, then you will not be surprised that the determinant of that matrix is just going to be the number itself, whatever it is, little a. Okay, that's for a 1-by-1 size. If I go up to a 2-by-2 size, so if A is a 2-by-2, let's say it has first row is A and B, and the second row is C and D, then how do we calculate the determinant of A in this case? Well, I'll give you the formula again. This is going to look familiar from last week. It is actually A times D minus B times C. You might remember when we were trying to decide which matrices were invertible. When the matrix is 2-by-2, I made the comment that an invertible 2-by-2 matrix should have AD minus BC not equal to 0. That's just going to be a couple pages back in your notes from last week, right? So AD minus BC not equal to 0. Well, we now see that that's consistent with this more general test for invertibility that I've put down here so far. Okay, so that's for a 2-by-2. Stop me if there's any questions. I'm kind of rolling through this fairly quickly. Let's go to a 3-by-3 matrix. See what we're going to say here. So now I'm going to have entries, let's say A, B, and C on the first row, and then the middle row is D, E, F, and the bottom row is G, H, I. And I'd like you to do me a favor if you're taking notes on this. Please leave a little bit of white space on the right of that matrix because I'm going to come back and fill something in there in a minute. But before I do that, let me just give you the formula for the determinant of A. Okay, so let's write it down here, guys. The determinant of this 3 by 3 matrix, it's going to be A times E times I plus B times F times G plus C times D times H, and then minus C times E times G, and then minus A times F times H, and then minus B times D times I. There it is. Now, usually what happens right about now is everybody starts to get nervous, like, how in the world am I gonna remember that? Yeah, because it's kind of an alphabet soup of 9 different letters, kind of in some sort of a contorted arrangements of 3 at a time. There is a nice way to remember this formula, and that is what I want to show you guys. And that's why I asked you to leave a little white space here. I'm going to show you the way to remember the formula. You don't need to memorize this. I actually never remember this. I just have another way of getting the formula right, which is what you want to do is take the matrix, guys, and recopy the first 2 columns just off to the right. So A, D, and G would be the first column, and the second column then is B and E and H. So just copy those first 2 columns off to the right. And what I am now going to do is try to explain where these 6 terms are coming from visually from this setup that I have here. Notice that A times E times I is literally just the main diagonal of the original matrix multiplied together. And I'm going to put a plus by that diagonal arrow because there is a plus sign in front of that term. Okay? And then the very next arrow to the right of that is B, F, and G. So you just translate to the right and make another diagonal that's parallel to the first one. And then you do that one more time and you get C, D, H. So your first 3 terms here are coming from those 3 arrows. You just sort of multiply diagonally down the matrix as I just explained, okay? You see that? A, E, I, and then to that we add B, F, G, and then the last one is C, D, H. Now, there's 3 more terms that all have minus signs on them. To see where those are in my little diagram, I just need to draw arrows going the other way. So CEG is actually right here. And I'm going to put a negative next to that arrow because that is a term with a minus. Okay. And then again, shifting one diagonal to the right, I get the AFH term. And one more diagonal to the right, I get the BDI term. So this is all that I ever remember. And there's a name that I give to this. I like to call this the arrow method. So this is the so-called arrow method. The diagram is arrow method for 3 by 3 determinants. Yeah, so that's called the arrow method for finding a 3 by 3 determinant. Every semester that I teach this class, there's somebody who decides to try to do a 4 by 4 arrow method. Doesn't exist. So don't let that be you. You're not going to be the one who makes a 4 by 4 arrow method. It's only for 3 by 3s. It doesn't really work for 4 by 4s. Just like when we were talking about inverses for larger matrices, we ultimately had to come up with a method for it. We didn't really have a formula for A inverse. We just had to follow a procedure. We're now going to find ourselves in the same boat with determinants, which is we just need a method for finding the inverse of, the determinant of a larger matrix rather than a specific formula. But hopefully everybody's good with these 3. Now, here's the beautiful thing about Friday's homework assignment. If you take a look at Friday's homework assignment, I don't think there's a matrix on that assignment that's bigger than 3 by 3, which means that it's fast because all you got to do is plug and chug with the formulas to calculate the determinants. There's a couple of the questions that ask you, is the matrix invertible or not? And instead of using one of the first items in black over here, what they want you to do on Friday's homework is decide if the matrix is invertible by using the test for invertibility that we're just now explaining. So you're just gonna find the determinant of the matrix, and whether it's 0 or not governs whether it's invertible or not. You see? Anyway, I do think that Friday's homework is pretty fast, even though there's a fair number of problems on it. By the time we get to the homework for next week, though, we're gonna see some larger matrices. So I would like to now, I've talked about 1x1s, 2x2s, and 3x3s. I would like to explain determinants for larger matrices. So what if A is 4x4, or 5x5, or 6x6, etc. That's kind of the next question I want to go over with you guys. And again, I don't have a one-size-fits-all formula for these determinants. Instead, we have to kind of do a little background and get trained up a little bit on how to work with this. So I have to make a definition here. And I'm going to talk about something called a minor of the matrix. So if, the IJ minor, I'm going to write it like this, guys, I and J in parentheses. The IJ minor, which is going to be denoted M sub IJ of my matrix A, which is an n by n matrix, right? It is going to be the determinant. We've just been learning how to find some determinants already, but this is going to be the determinant of the n-1 by n-1 submatrix. The submatrix obtained. So submatrix just means a smaller matrix. You see one less row and one less column than the original matrix A. We will have one less row and one less column. And what we are going to do is we're going to obtain this submatrix by deleting row I and column J. That's it. We're going to cross off one row and one column, which is going to leave us a smaller matrix. And we're going to then take the determinant of that smaller matrix, and that's the minor that goes with that particular I and J. Let's write down an example here. So let me take a 4x4 example. So let's just say that A is the following matrix here. So A is going to be the matrix whose first row is 1, 2, 3, 4. And then on the second row, I'm going to have -1, 1, 5, and -2. The third row is going to be 0 and 3 and 0 and -1. And the fourth row is going to be 2 and -2, and then 1 and -3. This is a 4x4 matrix. Now, just to be really clear about this, guys, there are 16 different minors for this matrix, because the I and the J could be any numbers, any row or any column, right? And I have 4 rows and I have 4 columns. That's actually 16 different combinations. We can see 16 numbers in the matrix, actually. So won't be surprised that it's a pain to calculate all those minors, but each minor of this matrix, each minor will be a determinant of a 3x3 submatrix. And I already know how to do 3x3 determinants, right? I can use my arrow method to find those 3x3 determinants. And so therefore I can find all these minors. Let's just practice one of them, okay? I'm not going to do 16 of them right now. Let's just practice one of them. Let's just find the 3-4 minor, M3-4. So using this notation, right? So that just means that the I value is 3 and the J value is 4. I is 3 and J is 4. So let's see, what does it say here? It says that I'm supposed to delete row I and column J. In this case, that would be row 3 and column 4. So I'm gonna cross off row 3 and I'm gonna cross off column 4. If I delete those particular rows and columns, I am left with a much smaller 3 by 3 matrix. So for my solution now, M34 will be just the determinant of the matrix that is left over after I've crossed off the row and column as you see in that picture. So 1, 2, 3 on the first row, -1, 1, 5 on the second row, and 2, -2, 1. Okay, and this is a 3 by 3. So if you were wondering why I didn't stop to do an example of the 3 by 3 arrow method, it's because we're gonna do it right now. Here is our 3 by 3 matrix. We're gonna take the determinant of this. I'm gonna go ahead and recopy the first 2 columns, as I kind of suggested there a moment ago. I'll recopy the first 2 columns of my 3 by 3 matrix, and I'm gonna start drawing my arrows and doing my calculations, okay? So let's see if we can figure this out, guys. So the first arrow goes right down the main diagonal, 1 times 1 times 1, which is just 1. And then I'm gonna add that to the next arrow over to the right, just parallel to it, 2 times 5 times 2, which is 20. And then I'm gonna go just one more arrow over to the right, one more diagonal to the right. We have 3 times -1 times -2, which is 6. And then I start subtracting the arrows that go the opposite way. So I'm just reminding you that I'm using this method right here, the arrow method. So now if I go the other direction, 2 times 1 times 3, that's 6, but now we're subtracting the 6, right? And then we're going to subtract the next diagonal, which is -2 times 5 times 1. So we're subtracting -10. And then the last diagonal, if I shift over to the right again, we're subtracting 1 times -1 times 2, so we're subtracting -2. Be careful about the negatives. Sometimes determinants can be a little bit challenging, just keeping the signs straight, because you can have double negatives, sometimes even triple negatives will come up. So we just have to be a little bit careful with that. Anyway, I've got 6 numbers here to simplify, and I guess the 6's cancel, and what am I left with? 1 plus 20 plus 10 plus 2. That should be 33. That should be 33. Now, is everybody with me? That's not the determinant of A. Let's just be clear. That's not the determinant of A yet. That's just the determinant of the submatrix of A. I still have to explain to you, how do we get the determinant of A from all these minors? That we haven't gotten to that yet. So won't get ahead of ourselves too much here. But at least we hopefully have at least a little idea how these minors work. We're gonna practice them a little bit more. But most of this is just kind of computational, simple arithmetic things. So, don't expect me to spend a huge amount of time just crunching out these 3 by 3 determinants, but yeah, for sure we need to be able to do this. When we actually come down to it and we're ready to ask how to find these larger determinants, it's not actually the minors that are ultimately going to tell the story. It's something related to that. And what it is something called a cofactor. So I need to make another definition here. And this is going to be something called a cofactor. So let's write it down. Get the correct page of my notes here. That would help. Yeah, so let's write down the IJ cofactor. So we have the minors, and now we're going to do the cofactors. I'm going to label the cofactors with Cij of my matrix A, which is an n by n original matrix, is, this one's pretty easy. To find a cofactor, Cij, I am actually just simply going to find the minor Mij and maybe do a sign change on it. Maybe. It depends on I and j. Some values of I and j, we will change the sign on our minor. Some values of I and j, we're just going to leave the minor the same as the cofactor. And here's how you get it right. You basically take -1 to a power of I plus j. I think everybody would agree, would you not, that if you take powers of -1, you're either going to get +1 or -1. And it flips back and forth depending on whether the exponent is odd or even, right? So -1 to an odd power is -1. -1 to an even power is just 1. And we're going to take that sign, whatever it is, either plus or -1, and multiply it by the minor that goes with it. So it literally is just take the minor that you already calculated and maybe switch the sign depending on whether I plus j is odd or even. So if we go back to our example again, just go back to the example from above. I guess I'll write this here. The example above, we could ask, what is the 3,4 cofactor? C34. And what do you guys think? The 3,4 cofactor is just the 3,4 minor. What did we get for that? 33, right? So it was 33. And do we need to make a sign change on the 3,4 cofactor? What is 3 plus 4? 7, right? Is that even or odd? That's odd. -1 to an odd power stays -1. So yes, we actually do need to make the sign change. It's negative of M34, which means it would be negative of 33. To tell you the truth, I don't actually usually use this formula so much. I have a different system for remembering my sign changes, and it's just a little diagram. I'm going to draw it for you. If it helps you, great. You don't have to use it, but I think it's kind of handy, which is I just draw myself kind of a big little plot of a matrix here. And I just kind of go through the entries and I put pluses or minuses depending on whether there should have been a sign change in that position. So for example, the upper left corner of the matrix, that's the 1, 1 entry. I is 1, j is 1. If you add those together, you get an even number. Even numbers do not have sign changes. So I would just leave it as it is. So I'd probably just put a plus there. Okay. And then, but if I then move to the 1, 2 position, well, that adds up to an odd number, so that will have a sign change. So will the 2, 1 position. But the 2, 2 position will not. And actually, what you start to realize after a while is that all this is, guys, is an alternating pattern of pluses and minuses. Right? It just goes like that. I mean, it could be any size, right? So if I'm looking at the 3, 4 cofactor, I'm looking in row 3, column 4. I see the little negative there. That reminds me, okay, I need to do a sign change on my minor. Whatever the minor was, I have to change the sign of it. Okay? I know some of this is kind of like, sounds very cookbook, very procedural. It's like, well, why do we do that? Who came up with cofactors? All these kinds of things. It really is kind of a little bit deeper than I want to get into here. And certainly we're leading up to a big result, which is to explain how to do determinants of larger matrices. So it's certainly well motivated. There's certainly a reason to want to do this, but it turns out like why and how it all works underneath the hood of the engine here. Well, some of that might have to just wait for another class. You guys will all be math majors by the end of the semester. If I keep doing my job, hopefully good. And then if that's the case, then you'll learn about it for sure in Math 307, which is our linear algebra class for math majors, a little bit more advanced course. Anyway, are there any questions so far? Please, Gabriel.
So we're allowed to choose I and J, right?
Well, not here. Like, here's the question: find M34. We are forced to live with whichever. I mean, you can find whichever minors and cofactors you want, but you know, there might be a question asking you for a specific one. Yeah, but I'm going to come back to that point about choosing. You might be wondering right now, am I going to have to find 16 different cofactors in order to find the determinant of this matrix? Turns out the answer is no, you don't have to do that You don't have to do all of those cofactors. What do you actually have to do? Well, that's what the next theorem is going to tell us. Okay, so we're about ready to really explain the biggest theorem of the day, right? So I'm going to do this. I'm going to do this big theorem, and then we'll try a full-blown example before we take a break today. Okay. So this is the big theorem. It is called. We've got two big theorems today. The invertible matrix theorem, of course, is huge, and now we have this one. This is called the cofactor expansion theorem. Really, really important theorem about determinants. Okay. What we're going to do here, guys, is we're going to let capital A be equal to an n by n matrix. This theorem, my friends, is going to give us a formula for the determinant of that matrix. This is what we've been waiting for. And I should point out that actually this formula, this theorem, is actually also true even for a 2x2 or a 3x3 matrix. It's just that for the smaller matrices, we have sort of a faster alternative here that we've already talked about. So this is maybe a little bit more work, but it does still work, even if n is 2 or 3 or even 1 for that matter. So what does the theorem say? Well, it's going to be not just one formula for the determinant of A, but an entire collection of formulas for the determinant of A. So I'm going to go 2 lines here, guys, just so you know what I'm about to write down. I'm going to have 2 lines written down. The first line, I'm going to write down little a sub I1 times the cofactor ci1, and then plus little a sub I2 times the cofactor ci2, and plus dot, 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 plus all the way across to ain cin. Okay. I'm gonna have to erase just a little bit more here. What you'll notice with this formula, guys, is that the first subscript is always an I. Now, that means, remember, the first subscript is referring to a row. So these AI1, AI2, AI3, those are just the entries of the ith row of our matrix. And what are you doing? You're multiplying them by the cofactors associated with that same ith row. So we could call this expansion on row I. I'm just going to call that expansion on row I. And now I come back to Gabriel's point, which is, do we get to choose what I is? The answer now is yes. The answer now is yes. This is the correct formula for the determinant of A, regardless of which row you choose to work on. So, half of you could choose I equal to 1, and the other half of you could choose I equal to 2. I could choose I equal to 3. We could all have a different row. We do the calculation of the determinant. We should all get the same right answer. Okay. And in fact, it goes further than that, which is you don't even have to pick a row. You can instead go for a column. So I'm going to do another line here where I talk about expansion along a column. The way that might look in the notation would be A1J C1J plus A2J C2J and plus dot, dot, dot up to ANJ CNJ. And this one, I'll just add on the end here, this could be thought of as expansion on column J. Expansion along column J. So you can choose any row or any column that you want. Now, they may not all be equally good. And one of the things you're going to want to practice a little bit is making a good choice of a row or a column. So again, I'm not going to prove this theorem here. This is a sort of a Math 307 thing on the level of proving it, but this is a powerful technique for finding determinants of larger matrices, 4 by 4 and larger. Okay, so let's actually do it with the matrix we already had up here. So let's make another example here. Again, I'm going to take A to be the same exact 4 by 4 matrix that we were looking at a moment ago. So 1, 2, 3, and 4 goes on the first row. The second row is -1, 1, 5, and -2. The third row is 0 and 3, and 0 and -1. And the fourth row is 2, -2, 1, and -3. And this time, what I hope to do is I actually want to find the determinant of A. I'd like to try to find the determinant of A. So it's 4 by 4. We're going to use this cofactor expansion theorem here. You've got 8 choices for how to expand it. You can expand row 1, you can expand row 2, row 3, row 4, or you could expand column 1 or column 2 or column 3 or column 4. Does anybody have a gut feeling about maybe a good choice of a row or a column to take advantage of here? Seth,
Row 1.
you like row 1. Why do you like row 1? The numbers are so nice, 1, 2, 3, and 4. And the 1, 2, 3, and 4 would be these A values, right? Josh,
Row 3.
why do you like row 3?
Has 2 zeros.
The zeros in row 3 are kind of nice because, after all, if 2 of my A's are 0, then over here when I'm calculating the cofactor expansion, I don't have to calculate the cofactors that are going to end up getting multiplied by 0. That's actually, from a workload perspective, probably your best bet, right? So I would probably go along with that and suggest that we focus on row 3. Not that you have to, but because any row or column will work. But if you want to have the minimum amount of work to do, I would choose row 3. And it's a good idea, guys, when you're doing these. Again, this won't be until next week's homework, really, but it's a good idea to tell me which row or column you're expanding. That's very helpful. So I'm just going to say here, I'm going to expand on row 3. Okay, so the first thing I'm going to do is kind of just spell out what my determinant formula would look like for the third row. So I'm up here on the first equation with I equals 3. So that is going to be A31 C31 plus A32 C32 plus A33 C33 plus A34 C34. So I'm just literally plugging in I equals 3 as subscripts all the way across that first equation, which you do need to learn, by the way. Okay. Now, the beautiful thing about this, guys, is that A31 is 0. And A33 is also 0. So 2 of the 4 terms, you don't even have to blink an eye. It's just automatically 0. You don't have to think about those. Let's go ahead and simplify what we have left. Actually, so there's one other thing I want to do, which is I always worry with this, that I am going to forget to do my sign changes. We do have to be a little careful about that, because in a minute, we're going to have some minors to calculate. And as soon as you get the minor, sometimes we have to do a sign change and sometimes we don't. The way to sort of front load that into your brain so you don't forget to do the sign changes is to do it right now, okay, at the beginning. So the A32, for example, that is a 3, right? But C32, does this need a sign change? C32, look at my diagram, guys, right here, row 3, column 2, there is a negative there. That means I need to do a sign change. So you know what I like to do? I like to just put the sign change in now. And then, of course, that means I'm rewriting it as M32. Okay? Agreed? A34 A34, that's this last term, that's a -1. And then I have C34. Do I need a sign change on the C34? I sure do. That's the other one that's circled over here, right? 3,4 is right here. So I do need a sign change on the 3,4 cofactor. So I'm gonna go ahead and put the minus on that as well. Let me just stick another negative here. And then M34 goes there. Now, by the way, in case you're keeping track, we already did M34. So we will be able to just plug that number in directly. But I do have one other minor that I didn't calculate yet. So we're gonna practice the minors again on this M32 example. So let me just move this over to here so I can record nicely the rest of this on this board. Everybody with me? Okay, so just have to, the number one mistake that people make with determinants tends to be sign errors. And, don't beat yourself up about that if it happens to you occasionally. I'm not gonna beat you up over it. If you do everything right, and you know what you're doing, and you make one small sign error, it's not going to totally ruin your exam or anything like that. So you just have to kind of do the best you can. So let's just keep going here. We have a -3 and then M32. So I'm going to, this is row 3, column 2. So I'm going to take this -3 and eventually I have to multiply it by the determinant of the 3 by 3 matrix that is left over after I remove that row and column. And actually, this is the number 2 mistake. Well, sign errors are common. The other thing that's common with this chapter, to be honest with you, is just simply miscopying a number. So just really have to make sure that every number was copied correctly here in that matrix. And then don't forget, we also have another term. Now this one already has a double negative on it, and it's plus M34. Now M34, we already have that worked out. So we're adding this 33 that we calculated earlier to get that portion of it. Slow me down if anything's not clear.
Isn't it -33? Because of
So C34 is -33, but you see, I already took out the minus and turned it into a minor again. So the minus sign switch, I took care of it right here. You wouldn't have had to do that. You could have just, from right here, you could have said A34 is -1 and C34 is -33. And then you still end up getting the 33 here. Either way, whichever way you like more. Okay. To do this 3 by 3 determinant, I'm gonna go use my arrow method again. So I'll recopy the first 2 columns like I was doing earlier. Do it carefully, and I'm gonna draw my diagonal arrows just like I was doing before. So what do we have here, guys? We have -3 times, and then get some brackets going for yourself. I'll put the plus 33 on the end here. In these brackets, I'm gonna draw I'm gonna write out my 6 arrow terms, right? So the first arrow is 1 times 5 times -3, that would be -15. The next arrow is 3 times -2 times 2, which would be -12. The next arrow is 4 times -1 times 1, that's just -4. And now I have arrows going the other way that I have to subtract. 2 times 5 times 4, that would be 40, but I have to subtract that. Subtracting 40. And then the next arrow to the right of that is 1 times -2 times 1, which is -2. I have to subtract -2. And lastly, I have -3 times -1 times 3, which is 9, and I have to subtract 9. Just like that. Am I going okay so far with the speed of this? It's a lot of just arithmetic. Actually, not that bad, not terribly conceptual. So I have -3 times whatever this is. I have to figure it out. -15, -27, -31, -71, -69, subtract 9 from that, negative 78. So it's negative 3 times negative 78, and then at the end of all that, we have to add 33. 3 times 78 is, I believe, 234. And we add 33 to that, and we get to our final answer, 267. Yeah.
Question I have is, why did we do cofactors again? Like, what's the purpose of
To-
changing the M34?
That's all the deep stuff that's buried underneath the theory of this, and ultimately, we need the cofactors because that's what's in this theorem. So this theorem says you have to use the cofactors to expand along a row or a column to get the determinants. So that's the reason we're doing it, but as I said, I am shoving a little bit under the rug as far as like where all of these formulas come from and stuff. It's just not something we have time for here. Everybody good with this though? So question, is this matrix invertible? As a follow-up? Not zero, right? As long as the determinant is not zero, then this is invertible. So I'll just say not zero implies A is invertible. So you might be thinking right about now that this is an awful lot of work to get a number that's either zero or not zero to make a decision about whether it's invertible or not. I'm not sure. I think I want to go back to EROs. Maybe I want to go back to EROs. I don't know. It's kind of it's a pick your poison thing. Like some people really eat up the EROs. They're really comfortable with those. Other people are like, I don't want EROs. I'm happy to do cofactors. Right? So you sort of get to make a choice in that sense. There's been a lot of research done, actually, particularly in the computer science world, about what is the fastest way to decide if a matrix is invertible. Should I just do the Gauss-Jordan method? Should I just do the EROs? Or in the long run, are determinants actually going to be faster? Turns out it really depends on the size of the matrices. As the matrices get really big, determinants become horrible. They become horribly long. Think about it. If you had a 5 by 5 matrix, even just 5 by 5, and you want to expand on a row or a column of your 5 by 5 matrix, keep in mind you'll go all the way across that row or all the way down that column. You'll be doing 5 cofactors, each of which is a 4 by 4 submatrix. In other words, each of which is as much work as what's right here. So you take this much work and you multiply it by 5 to see how much work it would take to do a 5 by 5 determinant. And then you can imagine 6 by 6, 7 by 7. It gets really, really unwieldy in a hurry. So it's not maybe clear which is the better way to do things, right? I do want to give you a little, I'll call this my soap opera hook to get you to come back again. There is going to be more to this number than just whether it's 0 or not. Like the 267 is going to mean something that I'm going to be explaining as we go forward. We're actually going to find out on Thursday that not only will this number tell me whether my matrix is invertible or not, it can actually help me find that inverse. It can help me solve systems of equations, and it can even answer geometry questions, right? Things that we can touch and feel and see. So I will get back to that. So as one little selling point for any skeptics out there who feel like this is a lot of work just to get this one number out of the answer, that there is some real value in the actual number. We're definitely going to come to that. But I mentioned a 5 by 5 determinant. So, which, as I said, in theory would be about 5 times more work than this. So I thought maybe we would do just one of those and see how it goes. Okay, is that all right with everybody? Nobody has anywhere to be, do they? Yes.
Couldn't we just use like row operations to make like the upper triangle and then just have a 0?
Did everybody hear that? If your matrix has lots of zeros in it, you're gonna be a happy camper, right? Because then you can expand on a row or a column that has a lot of zeros. And in so doing, you will get rid of a lot of the work. Like here, we only have to do 2 out of the 4 cofactors because there were 2 zeros here, right? So what the suggestion was, if you guys caught that, is could we use EROs to bring more zeros into the matrix, right? And then from there, have an easier time of doing cofactor expansion. That is an excellent strategy, and I'm gonna talk about that. It turns out that you can't just do EROs for free. When you do an ERO, it's gonna cost you something in terms of what the determinant is. So if you had a determinant you were trying to calculate and you do an ERO to that matrix, well, now it's a different matrix. It's gonna have a different determinant, and you gotta, be aware of that. But the prices that you will be paying for those EROs are actually things we can keep track of. I'm gonna come back to that. But before I do that, I just wanna play dumb for a minute. I'm gonna give you a 5x5 matrix, and I wanna do this calculation, and then I promise we'll take a break after this. So let's let A be this matrix right here, 3, 6, 8, 9, 1. And then the second row is going to be 0, -2, 5, 5, 3. And then the next row is going to be 0 and 0 and 5 and 2 and 6. And the next row is going to be 0 and 0 and 0 and 3 and -4. And the last row is going to be 0 and 0 and 0 and 0 and 1. Okay. So I'm trying to show you here, guys, the beauty of having a matrix with a lot of zeros in it. Yeah. Because what I'm gonna do, even though it's 5x5, I am going to calculate the determinant of A, and it's gonna take me less than 5 minutes. Okay, we'll be able to do this pretty quickly. Well, as long as you guys give me the right answers. Otherwise, we could be here all day. So when I say the right answers, let me ask my question here. For this matrix, does anybody want to propose a row or a column that would be good for expansion? The last row or the first column, either one. So let's just expand. You know what, I might just expand column 1. We expanded a row on our last example. Let's just do a column this time, just to mix it up. So I'm gonna go all the way down the first column and expand it using the cofactor expansion theorem formula, right? So my determinant of this matrix, how does it work again? Well, going down the first column, it's going to be 3 times C11. And then the rest of the column is a bunch of zeros. And just to really emphasize the alternating nature of the pluses and minuses, I'm going to write -0, +0, -0, +0. See, you have minus, plus, minus, and plus. So just kind of keep track of that. Okay, but obviously you don't really need any of that. It's just this first part that matters. So I have this 3 here. Now for C11, do I need a sign change on C11? 1 + 1 is 2, or another way to think about it is you've got the plus sign right here. Right, so you don't do any sign changes, you just leave it as is. And all I have to do, guys, is cross off row 1 and column 1, and it leaves me with this 4x4 submatrix. And again, I ask you, for the submatrix, I need to find that determinant. What would be a good row or column to use here? I could go with the last row or the first column. I'm going to stick with the first column just because that's what I've been doing. So the first column starts with a -2. Well, I should put brackets here. There's a -2 times, again, C11. And then, again, going down this column, -0, +0, and -0. And again, all of this doesn't matter. And you now have, if I simplify it, you have 3 times -2 times C11. And by C11, I actually mean, if I cross off this row and column, I just mean this little 3x3 right here. This is just a 3x3 right here. And if you can, at this point, you can punt and do the arrow method, right? You can just bail on everything, or you can keep going. You can keep doing the expansion along first column or third row. I'm just going to tell you that what will happen, so I'll just put dot, dot, dot here. I don't think I want to spend all the time on this, but if you do that 3x3 determinant, you will get a 5 and a 3 and a 1. Yeah, that's what you're gonna get. And at the end of the day, you multiply all of those numbers together. And as you can see, well, this is just gonna give you some value. It looks like it's -90. Yeah, it's another invertible matrix. But again, the question is, what does the -90 actually mean? I'll come back to that. But the point is, I got this determinant just from these 5 numbers. Does anybody see where these 5 numbers are? Just the main diagonal of the original matrix, right? These numbers right along here. And that is not an accident. That is always going to be true. I'm going to state it here as a theorem, and then we'll take a little break. Which is, so let A, which is n by n, be upper or lower triangular. So you start with a triangular matrix. Then the determinant of A has a really nice formula. So I think I lied to you earlier, by the way. I think I told you on Friday's homework, all of the matrices were 3x3 or smaller. I think I forgot, there's a couple of bigger ones. But guess what? The bigger ones are triangular. And this is so super nice. You want to know what the formula is? It's just simply multiply the main diagonal entries. A11 times A22 times A33 and dot, 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 up to ANN. That's it. Super easy. Super easy. And we have enough zeros in a triangular matrix to give us a super fast way to get the determinant of that matrix. So we come back to the idea that was proposed a few minutes ago. Could we take any matrix and use EROs on it to bring it into this kind of triangular form from which we could then immediately get the determinant straight from the formula? And that's something we're going to explore on Thursday. But I think I've given you the nuts and bolts, the highlights of how to do these determinants. Is there any questions so far? If not, during the 10-minute break that we're going to take right now, if you have any more problems, again, I do not have office hours tonight. So if you do have anything else from tonight's homework that you'd like me to do for you, I'm happy to spend the last part of class doing. We're not going to do any other new material today. So we can answer any more homework problems. I also have a group work that we're going to talk about. But let's take 10 minutes, and at the bottom of the hour, we'll pick up and do those 2 things to wrap up today. See you guys in a few.
Hi, how are you? Good. Really?
Yeah.
Second line. Same, I'm like, I think yawning.
Oh, that's right.
That's too long.
Biz today. Another one of these. It's a great. Just can't wait for the next.
Chilling. How was your weekend? Good. Yeah. Yeah, it's very different. Good. I mean, yeah. Yeah. It was, yeah. I saw a picture. I saw the flyer for the audition. Yeah, yeah, everybody has their big. Like, yeah. Coach said, we'll have another week. But, yeah, it's, yeah. Yeah, it's crazy. It just all happens. Everybody, yeah, yeah, everybody's, I bet, man. There are a couple of them who came to switch sections. So I can only imagine how stressful it is. If you go close to your section, right? Yeah. Are you worried for certain members not doing that? Oh, yeah. Yeah. And also, my friends go to different groups. Like a lot of them also didn't make it. Oh. All these like kind auditioning. But that's just how. They usually do, like, at least the big ones, so. Like, just the stuff. In my stuff. I like to go with different teams. Which I think sometimes is like, yeah, usually it's like. At least they're kind of theory, so I have to pick one, because it's just like. Right, right, yeah, you'll make it. That's how to figure out. Yeah. Are you on the ticket one? Yeah, yeah, because it all happened. Oh, okay. So. Although I would have chosen to if I had the option. Yeah. Dang, that's nice. It's super intense. And like, I mean, there's people like that fly out of state. Yeah. People from different countries. Yeah. Express thought, I advise people. Yeah. They do. Something means, how's it going? Good. What are we doing? Unpredictable, double A, okay, you just chilling?
Mostly.
Okay, cool.
I got the homework done for Monday, so.
Cool.
Please with that.
Oh, wait, like this Monday?
Yeah.
Oh.
Actually, wait, I got it done Monday night. Yes,
Okay, okay,
trying to,
yeah,
try to stay ahead if I can.
yeah,
I tried doing some problems from Friday's homework, but We don't carry on yet, so.
And. I don't know.
Yeah, honestly, there's like, because I want to do the fashions. Yeah. Yes. I was really trying to go with that. But then I didn't get it. Keep going. As long as you do it from here. It's easy to find. No, I didn't see. Yeah, I didn't see. You have one. This one, that's this one. Yeah.
Was good. Good? Yeah. That was yours.
Okay, I have a 4-day weekend every week. How could that be bad? I mean, not really. I have to grade papers and do other things, but most of my work is Tuesday, Thursday. Can't complain. Well, don't look now, guys. We only have 20 minutes left. Does it feel like the time just flies away sometimes? That was pretty fast. So just so you know, no more new material today, which means if you really want to hear about using EROs to put a matrix into triangular form so that you can do its determinant easily, you're gonna have to come back on Thursday. What can I say? What we're gonna do for the last part of our class today is I'm gonna answer a couple of these homework questions. And then I passed out a group work handout. I did mention that those group works would be a good thing to review for the midterms. So we won't have time to do this full sheet, but we'll, I'll hopefully give you 10 minutes to talk with some folks about it a little bit. So we'll just see how the time goes. But I do want to do the homework since I'm not going to have office hours tonight. Make sure everybody leaves here feeling super solid on it. Number 34, I always get this one, is that if you have a matrix that is symmetric, right? Let me just stop right there. This theorem, or this problem is about symmetric matrices. The theorem we just had over here was about upper and lower triangular matrices. Make sure you know some of these words, right? For the exam next Thursday, there was a special matrices handout that I also had a 7-minute video that went with that. It's in Canvas that talks about or reminds you what is a triangular matrix, what is a symmetric matrix, what is a skew symmetric matrix, and so on. So just want you to see that these matrices are showing up, like we're seeing them here. Anyway, so if we have start with a symmetric matrix, and if it has an inverse, so it's invertible, then the inverse matrix will also be symmetric. So the inverse of a symmetric matrix is still symmetric. Can somebody remind me what it means for a matrix to be symmetric? Ian? That's it. That's it. And that's what you have to know in order to do this problem and to really to understand symmetric matrices. So we are given that A transpose is equal to A. If I swap the rows and columns of the matrix, it stays the same as the matrix. Nothing changes. Okay, so we don't need to like write out the entries. We don't have to get our hands messy with the rows and columns. We can just do this very abstractly in this notation. It's the best way to do it. It's the power of abstraction, which, as somebody who did my PhD on abstract algebra, I have to be very much a proponent of, right? I really support these kinds of things, even though they're so short, right? Okay, so the transpose of A is equal to A. I would like to show that that same thing is true about A inverse. So what I'm going to do is try to write it out that what it would be. So if I take A inverse and I transpose that, okay, I need to fill in the gaps here, but give yourself a little room. I'm trying to hopefully, I'll put a question because we haven't shown this yet. I would like to convince you that if you transpose A inverse, you still get A inverse. That's what it would mean for A inverse to be symmetric. Now, does this look familiar at all? You seen that anywhere?
Algebraic properties.
Yeah, in last week's notes, we actually did a little theorem where I talked about a couple of these properties of inverses. So one of them was that if you take the inverse of A times B, you can do that and you'll get B inverse times A inverse. But then the second one was, well, if you take A transpose inverse, it's the same as taking A inverse and then transposing that. So the only sort of reference point that you have from anything familiar to start with this is to just take advantage of that second equation that comes from last week's notes, right? So I'm going to go ahead and do that right away here. So in the first step, I'm going to reverse the order of the transpose with the inverse. So just switch the two things around, yeah? And now the question is that the same as A inverse? Well, you're shaking your head yes. Do you see why?
Because the transpose of A is equal to A.
Yeah, this A transpose right here, we can just replace it right away with A on the inside, right? So we're given that A transpose is the same as A. So this is no longer a question. Let's erase that. And let's just make this an equal sign. Guys, it's the shortest problem you'll ever see. That's it. That's the whole write-up. That's the entire solution right there. Just this line. Okay, can't get much shorter than that. So yeah, so that is showing that A inverse is symmetric, right? So A inverse is symmetric. Absolutely true. Okay, very good. By the way, so you'll notice that inverses, they play nice with transposes. You can work with them using multiplication. I think there's a true false item F that says if A is invertible and B is invertible, then A times B is invertible. Well, that would be true. And this would be what you would want to write down on your paper. So this is for part F of the true false. You say true, and here's your justification. There is a formula for the inverse of A times B, and here it is. Right. But what you don't see here is anything about addition. Inverses of A plus B. And if it's not here, it's probably because it's not true. inverses do not play nice with addition. And so part E, which somebody put on the board over there, is actually false. And in a minute, I'll talk about it. In a minute, we'll talk about it. Okay, so anyway, but multiplication, it's true. Transposes, it's true. Okay, everything's good with that. But before we go any further, let's do 35 also. This is the other one that people want to look at. This one just says that if the 12th power of A is the zero matrix, again, this is the all zero matrix, everything is zero inside of it. Then they're asking us to do another little proof, which is going to be almost the same length as this one. Another little proof that the inverse of the identity minus A cubed is actually equal to the identity plus A cubed plus A to the 6th plus A to the 9th. Can somebody remind me, how do we show that the inverse of one matrix is another matrix? We multiply the two matrices together, and what are we supposed to get if they are inverses of each other? The identity matrix, right? So what we're looking for, guys, if two matrices are inverses of each other, then when I multiply them together, I should get I. I think they're having you do that on a couple of the other homework problems on this assignment, but that's what we're going to do here as well. I'm going to take the matrix on the left, I'm going to multiply it by the matrix on the right, and see if when I crash them together that I get I, because that's what I'm supposed to get. Okay, so let's get the solution going here. I'm going to take the identity matrix minus A cubed. I'm going to by the way, I'm not putting the -1 exponent on that. I'm just taking the matrix on the inside, right? I'm going to take that guy, I'm going to multiply it by what the inverse is supposedly equal to. So this is like my X times Y in that notation, right? So first matrix times the second matrix. So I just need to work this out, okay? So the way you can do this is just to literally expand it as if it was a algebra expression from high school, right? It really is okay to do that. So the identity matrix gets multiplied by all four of these. Of course, when you do that, nothing happens because the identity matrix, if we remember, that's like multiplying by 1, doesn't change anything. So identity times identity is just identity, and then identity times A cubed is just A cubed. Identity times A to the 6th is just A to the 6th. Identity times A to the 9th is just A to the 9th. And now I have to distribute the negative A cubed to all four terms. So negative A cubed times the identity is negative A cubed. Negative of A cubed times A cubed gives me a negative of A to the 6th. Watch your exponents, guys. Be careful with that. And then A cubed times A to the 6th is A to the 9th. And I'm running out of room, but I'm going to squeeze it in right there. A cubed times A to the 9th is A to the 12th. And you kind of let the dust settle on that for a minute. Take a look at it. What do you notice that you can do? Simplify it how? Say it again? There's canceling, right? There's canceling. I've got A cubed canceling with A cubed, right? A to the 6th canceling with A to the 6th. A to the 9th canceling with A to the 9th. So we get rid of all those terms that can cancel. The only thing left is the identity matrix minus A to the 12th. Now we were supposed to get the identity matrix. That was what we were hoping to get on the right-hand side. But we didn't quite get that yet. And so what's the issue here that we need to address or to use? Yes, please.
Is it given that 8 to 12 is equal to 11 in your matrix?
Yeah, there's got to be a reason they told us this, right? So A to the 12th is 0. And so this just becomes, if you're subtracting 0, you can just forget it. And so you just get your identity matrix there. That's it. By the way, this would even be true, you don't need to write this down, but even if this was A to the 11th, still would have been the same exact write-up. Because if A to the 11th is 0, and then you multiply that by something else, which is another A, it's still 0. Okay, so if A to the 11th was 0, then so is A to the 12th. I've had students in the past, they've gotten mixed up because they didn't understand that the difference between the 11 and the 12 wouldn't have made any, it makes no difference really. So, but just so you know, the way this one was stated, this was a 12. Okay, awesome. Okay, I mentioned part E. Is everybody okay with that? Good on that one? I mentioned the part E about inverses not playing nice with addition. And that is actually right. It is a false statement. And I just want to explain what should you be writing down on this on your assignment. Remember, I'm not asking for a long essay or anything. When something is false, the best way to convince me is just with an example. If I make a false statement like all Saturdays are sunny, right? How are you going to disprove that? Like, how are you going to convince me that it's false? Well, you're just going to wait maybe for several weeks, but eventually there will be a Saturday that is not sunny. And you can say, see, here's my example that shows that your statement was not correct. It's like that here too. We would like to give an example to show that this is false. So what that means, guys, is I need to come up with a couple of matrices. So just to see what this says, if A and B are invertible, if A and B are invertible, so is A plus B. That is a false statement. You can start with two matrices that are both invertible, and by the time you add them together, maybe it's not invertible anymore, right? So to convince me, we need an example. Just one example is all you need. Is that?
A equals the identity.
Okay, you're giving me the example already. Okay, what size matrices are you gonna give me? With your example, I already know where your example is going. With your example, it wouldn't matter, but in general, can I get the pulse from the rest of the class? And what would you think would be like a good size to work with if you actually had to get your hands on some matrices?
2 by 2.
2 by 2, right? You know, you don't want it to be too big, but a 2 by 2 is already probably big enough. So we need a 2 by 2 matrix, and Seth is going to use the identity matrix, right? So that would just be for a 2 by 2, that would be this matrix right here. By the way, we know that this is invertible. If you do AD minus BC, it's not 0, right? So this is invertible. Now, is there somebody besides Seth who can give me another matrix that is invertible here, which I'm going to call B? Does anybody want to throw out 4 numbers? Give it a try.
1, 0, 1, -1.
1, 0, 1, and -1. That looks good. If I do AD minus BC, it's not 0. So this would be invertible. Now let's just calculate and let's just see what happens. Guys, sometimes you have to experiment a little bit. Just have to kind of play with it. If I add these together slot by slot, 1 plus 1 is 2, 0 plus 0 is 0, 0 plus 1 is 1, and 1 plus -1 is 0. That look right? Is this matrix invertible? If you do AD minus BC, you just get 0, don't you? And if that's equal to 0, then this is not invertible. Guys, this is great. This actually, we got lucky this time. It worked right off the bat. It worked right off the bat. So you started with an example of 2 matrices that were independently invertible, but after you added them together, you got something that was no longer invertible. Yeah, so that's kind of how that works. By the way, the other way to do this is to literally just take your favorite matrix for A and then just literally take the negative of it for B. Because after you add these together, it's a no-brainer that you have all zeros in the matrix, and the determinant of that is for sure 0. So you could make your example out of something like this too if you want. There's a million examples you can give. So as it happens, that turns out to be part 4B on the group work. So this handout that I just passed out, part B of number 4, just says, give an example that if A and B are invertible, then A plus B need not be invertible. So here you go, right? Here's a good example. And actually part A of that problem is basically just another version of this question. So we kind of did problem 4 on the group work. Can I just ask you really quickly? I think instead of doing it as a group work, since I only have like 2 minutes, I just want to talk through a couple of these. Let's look at number 3. So this is off of group work 4. Remember that the solutions to these are online. So if we don't have time to fully do them now, we should be able to look them up later. Is it true, true or false, guys? If A has more rows than B, the second, guys, more rows than B, would it be true that the rank of A is greater than or equal to the rank of B? That's pretty false, right? Remember, the rank is the number of pivots. Can you think about how you would explain an example of that? Again, it's false, so we should try to give an example. One more time.
So this thing, matrix like 1 by 3.
1 by 3.
Not 1 by 3. I'm sorry. By 3 by 4. 3 by 4.
How about just make some giant matrix that's all zeros? What's the rank of that? 0. There's no pivots, right? But then you could have this tiny little matrix B over here that has 1 number in it. And so this definitely has less rows than A does, but it has a bigger rank than A. So this is certainly this is false, and we've got no problem giving an example of that. What about part B? This one we can just talk through. I won't write it out. Is it true or false that the columns of the row echelon form that contain the leading ones, those are the pivots. The columns that have the pivots, do those go with the free variables? I think this is false also, right? Remember, when you have your row echelon form, the pivots are the leading variables. The free variables correspond to the non-pivots. Right, so the leading ones do not correspond. These are the leading ones here, right? Those are the pivots. They do not correspond to the free variables. So that's also false. And then part C, the last one I'm going to talk about, guys. If we take A plus B, 2 matrices, and we square it, is it true that that would be A squared plus 2AB plus B squared?
No.
That's also false. You guys were fast on that. What's wrong with it? Right, the matrix multiplication is not commutative. The correct answer would have been A squared plus AB plus BA plus B squared. Yeah, so that's also, so everything was false on that. Number 1 and number 2, those are just computational practice problems. I will leave those to you on your own if you want to practice using the row echelon form process. Take a look at that. All right, guys, have a great rest of your Tuesday, and I will not be around probably till Thursday morning, but Thursday we'll pick things up with the determinants again. I will see you then.
We're not doing this, right?
No.